I will begin with a word of prayer as I get up here. So, Dearly Father, we thank you for this day. Again, I thank you for this class and just ask you to guide our steps today, help us to glorify you, and just to learn a little bit more about sets and how to prove things, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get right into it. I have defined many things about operations on sets, but not everything, right? So here's another definition. So we're talking about set theory again today, basically. And so here's a definition that we should know. Sets A and B are disjoint. So we're defining disjoint. If A intersect B is the empty set. If A intersect B is not equal to the empty set, then A and B meet. So two sets meet if their intersection is not empty, right? Which is to say there's at least one point in their intersection. So an example, let's see here. So example 1, we could let A be like the natural numbers, right? And we could let B, say, be the open interval from, I don't know, let's say 8 to 13. All right, so here's 8, here's 13, right? This is the open interval, so it's like all these points from there to there on the number line, right? That's my B. How do you picture the natural numbers? It's just whole numbers, right? So it's got, I'll draw them as dots, right? There's like 7, right? 8, 9, 10. Starting to, my numbers seem to be getting slightly more compressed. Sorry, 13, 14, right? So here, certainly A and B, they meet, right? What's the intersection of A and B? Which points are in both sets? Yep.
9 through 12.
9 through 12. Right, so 9, 10, 11, and 12 is probably the best way to express that, right? So this is that roster notation we talked about last time. Notice that there's an incredibly large difference between these two different kinds of sets, right? Like the set A, it's called, this is an example of a discrete set, right? So the points are separated, you know? In contrast, B, you might call a continuous set. Some people might say that. But there's an infinity of points between 8 and 13 not included in that set, right? So there's that. Okay, so then we talked about set difference before, but I need to talk about complements. So here's the definition. If U is the universal set, or sometimes you might call it the universe of discourse, some people will say. And A, let's see here. My bad. B is a subset of U. Then the complement of B is B tilde, which is defined to be U minus B. I say in the notes I have the complement of B relative to U. You could add those words there, but sometimes you don't want to. You want to just talk about complement. So I'll put it in parentheses here, is relative to U. So set difference, if we take it with respect to one particular given universal set, we call complement. And I use the tilde notation for that. So like, let's see, an example of this. How about if we're letting our universe be the set of all real numbers, right? And let's let B be, I don't know, say the open interval from 0 to 1. What's the complement of B? So by definition, it's what? It's u minus b. But what does that mean? That means x, in this context, x in the reals, right? X and u, such that what? Such that x is not an element of b, but in this case, b is 0, 1, right? So we can express that in interval notation. How? What are we looking at? I'll get us started. Minus infinity, 0, and then union 1 to infinity, right? We always put parentheses around infinity because infinity is not a real number, right? So it's not included in the interval. There is something called the really long line where you can adjoin infinity to the real numbers and look at that, but that's not what we're doing. Anyway, so how about the 0 and the 1? Are they, do I need a square bracket there? Or do I need a open bracket? What do I need? Square bracket, right? Because neither 0 nor 1 are in the open interval from 0 to 1, so that means that they must be in the complement. All right? So there's that. Another good example, if we let the universe be the set of real numbers, and we can look at like the set we're complementing to be, say, the rational numbers, right? So what's the complement of the rationals in the reals?
The irrationals.
The irrationals, right. So this would be x in the reals such that what? X is not an element of the rationals, right? So I think I used the notation like that. There doesn't seem to be a well agreed upon notation for the irrationals. But you could say that. Right. Let's see here. How about this? What if I was to, example 4, what if I was to say u is the complex numbers, right? And I look at the complement of the real numbers. What would that look like? I would be looking at like what? A plus IB such that what?
B is not equal to 0.
B is not equal to 0. Very good. You might call this, I would sometimes call this like the set of genuinely complex numbers. Although I don't know if there's like a well agreed upon term for this. But that's what I would say in like, just everyday math speech. Yep.
Does there having, or with the universal set, does that mess with the Russell's paradox stuff about there can't be a set of all sets, or is this different?
We agreed not to talk about that.
Okay.
So the whole Russell's paradox and all of that business, if you actually study the Zermelo-Fraenkel axioms carefully, it will make some of the things I take points off you guys for illegitimate. So I can't talk about it because it'll make me hypocritical for the things I'm going to take points off of.
Okay.
Primarily that in the careful axiomatics, the division between set and element is somewhat blurred. But we will insist that a set is a set and an element is an element. And because that's just how mathematicians actually use set theory. But if you look at the axiomatics, it's kind of blurred. I really didn't want to say this. This is all your fault. Sorry, that was a pretty good non-answer, I think. But yeah, good thing to think about, though. Let's see here. So, where was I? Let's see here. All right. So here's a theorem. let A be, I mean, certainly what is the universe will change the answer to what the complement is, won't it, you know? So talking about complement is always a kind of context matters there, obviously, right? So anyway, here it is. If A is a subset of B and B is a subset of C, then what? You guys fill in the blank here? What do you think is going to be true there? A is a subset of C, right? So that's one thing that's true. Another thing that's true is A is a subset of A union B, rather. And also, part C here, the intersection of A and B is a subset of A. Part D, what do you guys think the intersection with the empty set is? What would it take for an element to be in this set? In order for an element to be in the intersection of A and the empty set, that means that the element is what? It's in both A and the empty set by definition. Is there any such element? No, there's no element in the empty set. So this by definition, then, so it's pretty clear that that's equal to the empty set. Let's see here. What else do we know here? Oh my goodness. We're going to be a while. E. All right, guys. Buckle up, I guess. A union the empty set. What do you think that is? A. Very good. How about A intersect A? What's that? How about A union A? What's that? How does A union B compare to B union A? Let's see here. So you guys already told me A union the empty set's is A again. A intersect A is A, yeah. A union A. These ones are, that's a little bit more open to interpretation, but what I'm fishing for here, and is in the notes, is that, by the way, that's also B union A, right? And this is also B intersect A. So the union and the intersection, they're both commutative, we could say, right? The order of intersection or union doesn't change the outcome. What else can I tell you? What happens if we remove the empty set from a set? What's A minus the empty set? A. How about if we take the empty set and take A away from it? What's the empty set with A removed? It's still the empty set. Sorry, my empty set has slowly but surely turned into a phi, so you'll forgive me. Or not, I guess. I don't know. Did you forgive me? Or you didn't? I missed it. Or you just heard me? All right, so A union B union C is A union B union C. So the English kind of lets us down here, but notice that the parentheses are in different places. So the union is associative, right? Union is associative. Guess what? Same is true for intersection. The intersection is also associative. Now this one's a little bit more interesting. N. A unioned with the intersection of B and C is equal to the union of A and B intersected with the union of A and C. You could think of this as kind of a distributive law of union and intersection. I mean, be careful not to prove that for you today, as that is your problem 31 in your homework, mission 4, to prove that. So I probably shouldn't do that in class. P, LMN O. Oh, my bad, that was O. Oh no, what have I done? Ah! That was O. I've neglected N. But I'll put N next. Okay, sorry about that. Which was the same thing, right? But what's the difference? See if you can see the difference there. We've swapped in N versus O. The unions are intersections, and the intersections are unions. So we have a distributivity of intersection across unions in this way. So O is the homework problem. N is one that's not your homework problem. So maybe we'll prove that one in class today here in a second. Continuing, I guess I'll put up here P. A is a subset of B if and only if A union B is equal to B. Q, A is a subset of B if and only if A intersect B is equal to A. So those are interesting because that gives us a way of characterizing subset in terms of equality with respect to union or intersection. Those are actually kind of interesting identities there. And let's see here. I'm almost to the end of this list, this monster list of identities. R, PQR. If A is a subset of B, then I'll put the conclusion down here. A union C is a subset of B union C. And finally, S here, if A is a subset of B, then punchline, A intersect C is a subset of B intersect C. I should be careful not to prove part S because that's your problem 32 in the homework. All right? So a lot of these are just kind of like obvious. We practically talked through them as we wrote them, right? Like I can talk through the proofs of a few more without writing anything, right? Like, what's the proof that A intersect A equals to A? Right? Let X be an element of A. Then X is an element of A and X is an element of A. Conversely, if X is an element of A intersect A, then X is an element of A and X is an element of A, which means X is an element of A. Those two sentences respectively prove that A intersect A is a subset of A and that A is a subset of A intersect A, which is to prove that these are equal by double containment. In other words, you can argue that A intersect A and A have the same elements, right? And we can do the same for like G and H and I. These are all easily proved by like one sentence. Yeah. But let us look at the proof of A. I won't prove everything here, but I'll prove a couple. Let's do A, because it's healthy for you guys to see how these proofs go. So like, let's do that. Our claim is that if A is a subset of B and B is a subset of C, then A is a subset of C. All right. So the proof goes like this. So here's the proof. This is a direct proof, so we're going to assume that A is a subset of B and that B is a subset of C. That's how we start. Right? So we assume the antecedent. All right. Then what? We say let X be an element of A. Then, since A is a subset of B, we find X is an element of B by definition of subset. Note, X is an element of B implies X is an element of C, since B is a subset of C. All right? Thus what? Thus X an element of A implies X an element of C. Hence, by definition of subset, A is a subset of C. There we go. That's how that goes. Any questions? So here, we didn't have to do any double containment here. Why not? This is not a proof about equality of sets, right? This is just this is a direct claim. We have these assumptions, and we're trying to make this conclusion, right? How do you prove something's a subset of another? You take an arbitrary point in the alleged subset, and you show that that point necessarily lies in the superset. That's what these arguments do. So, all right, let's see here. What else did I say I was going to prove? Which one was your homework? It was, oh, that was your homework. I should do n, right? Let's try the proof of n. I'll do it over here. All right, so what are we trying to prove in part n? We're trying to prove a set equality, right? So let's look at the proof of n. So here's how I'm going to do it. Let X be an element of A intersect B union C. All right? By the way, this is all done under the banner that we've already assumed A, B, and C are sets, so that's why I'm not writing it again. I hope you guys can forgive me for not writing that. Let's see here. Okay, so then what? What does this mean? Then X is an element of what? A, and X is what? Element of B union C, right? Agree? By definition of intersection, right? Okay, thus, X is an element of B, or X is an element of C, since X is an element of B union C, right? Definition of union is that it's in B or C. So what do we find then? Consequently, X is an element of A, and X is an element of B, or X is an element of A, and X is an element of what? C, right? But that shows what? Hence, X is an element of A intersection B, or X is an element of A intersection C. Therefore, X is an element of A intersect B unioned with A intersect C. Because it's in this set or that set. Right. If you'd like me to make the proof more verbose, in every one of these sentences I should either say by the definition of intersection or by the definition of union. I'm not doing that at the moment because I think you can probably see it more clearly if I don't write that at the moment. So. And also I'm lazy. But so what does this all show? What have we shown? We have assumed X is here, right? And now we have made steps that show that in fact X is there as well. What does that mean? Thus what? By definition of subset, we have that A intersect B union C is a subset of A intersect B unioned with A intersect C. Because we took an arbitrary point in the intersection of A with B union C, and we showed that it's in fact in the union of the intersection of A with B and the intersection of A with C. We are now at the 50% mark, all right? Because we're trying to prove, for part N, that these two sets are equal, right? So what's next?
So it's double contained?
Double contained, right? So we need to pick X where. Or you don't want to use X, we could use, tell you, I'm going to just flip the script. Y, we're going to use Y. Let Y, check this out, be an element of A intersect B unioned with A intersect C, right? So now we start on the other side of the alleged equal sets, right? Pick it in there. What's this mean? Then Y is an element of A intersect B, or Y is an element of A intersect C. Hence what? Y is an element of A and Y is an element of B, or Y is an element of A and Y is an element of C. But what does this mean? In both cases, Y is an element of A, right? Thus, Y is an element of A, and Y is an element of B, or Y is an element of C. Hence what? Y is an element of A intersect B, my bad, Y is an element of, let me say this, Y is an element of A and Y is an element of, I'll get out of the way here a second guys, B union C, right? So we have Y is an element of A and Y is an element of this or that, right? So Y is an element of A and Y is an element of B union C. So, consequently, Y is an element of A intersect, parentheses, B union C. But hey, that's what we were trying to show, right? Our goal was to show that Y was there. Yeah.
Is there any difference between thus, hence, consequently, and therefore? Or can you use them interchangeably?
Style, I suppose. But yeah, pretty much they're interchangeable. I try to save therefore for like the end, but you know, I don't have a good answer to that question. But that's a fair question. I just try to use, I try not to use the same one over and over and over again, just as a matter of, not being too boring in the writing. But logically speaking, yes, you could just be thus, 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 hence, hence, hence. But like if you turn a paper like that into a journal, the reviewer is going to complain. I mean, I got a paper back. I turned this paper in like 2 years ago. I don't know. Is it 2 years ago? A year and a half ago? I don't even remember when I submitted this stupid paper. I got 3 reviews. The one guy wants it to be completely rewritten. We're using different methods and different examples. It's just like, so you want me to write your paper, not the paper I wrote. That's lovely. Why don't you go write that paper? Don't ask me to write a different paper. I wrote a paper. You didn't say, no error, like no mistake in the paper, nothing's wrong, just I want you to write a different paper. That's the worst kind of review. Then the guy in the middle, he's like, you need to put periods at the end of your equations. I'm like, I can do that. Fine. I add periods. And then the third guy wants like me to talk about future work in other directions in like a concluding section. I'm like, and reword the abstract. I'm like, okay, the third guy, I can deal with that. The first guy is impossible. So what I'm going to do is I'm going to take everything the first guy said to do. I'm going to take all of that. I'm going to fold it into my future direction section. So I'm going to use the first review to answer the third. And hopefully if I get 2 reviewers on the side, that'll be enough to publish it. And then I can forget about this thing, which would be lovely. I love math, but like once you've written a paper, like sometimes you just want to like be past it, Maybe you've experienced that with other classes, right? You write a paper and you've had enough of that topic for like the foreseeable future. Oh, conclusion. Let us not forget the conclusion. Hence, I probably should say therefore, but anyway. A intersect B unioned with A man, if I could not write intersection when I mean union. A intersect C is a subset of A intersect B union C. Here I'll use the therefore. Therefore, A intersect B union C is equal to A intersect B unioned A intersect unions. If I could just use my words today, it would be lovely. A intersect C by double containment. There we go. So the argument I had to make for like homework problem 30 for you guys was somewhat similar to this. Like I had to use double containment to establish that your problem 30 in your homework. But so anyway, you have more chances to try out your hand at proving things about sets in mission 4. So there's that. All right. Any questions? Do you guys understand the big picture here? So like in this kind of proof, if you're like me when you started all this stuff, you'd just be like, I'm kind of lost. I don't know what I'm doing. And so for me, as a guide for a proof like this, what was helpful was to look at a Venn diagram. Because if you look at the Venn diagram, you can kind of see where you are and where you're going. So like if I can, so we've got what? We've got B, we've got C, right? And sometimes if you look at that, you can kind of see how the proof works. Like we're supposing that it's to start with, supposing that X is in the intersection of A and the union of B and C, right? It's A with the union of B and C. So basically that's in here, isn't it? So it's in A intersect. So B and C, it's everything within the green and the blue circles, right? So the set we're talking about basically is this, right? So you might be able to see things from that picture if you think about it. So like if X is in A intersect B union C, that means it's either within the blue part or within the green part. That was like what we said in the first sentence, essentially. Going that way. The other way, we're taking Y in the intersection of A and B union C. I don't know, they both look the same to me in the picture. My point is, if you draw the picture, you might be able to see like what you're missing, is all I'm saying. Also, I don't think I drew the Venn diagram for 3 sets before last class, so here it is. Do you guys know how to draw the Venn diagram for 4 sets? Ever seen it? Ever wonder why? Because it's impossible. You can't do it. You can't draw 4 circles whose intersection gives you like all possible contingencies. No matter how you draw it, it's not possible to draw the 4 circles so that all the different subcases are all illustrated by subparts of the graph. Yeah?
Could you do it by spheres in a 3-dimensional?
Can I draw a 3-dimensional Venn diagram with spheres?
No, I'm just saying, would it be possible?
Well, it wouldn't be a Venn diagram then, because a Venn diagram is by definition like made from circles in the plane. So, can I illustrate logical contingencies with higher dimensional, subsets of a higher dimensional space? Sure, yeah. But that wouldn't be a Venn diagram. There is a way to draw a Venn-like diagram for 4 sets, but you have to use like a sliver, like some kind of like, not a circle, but some kind of bendy thing. Search it up after class. You'll find the picture. Don't ask me to draw it. I can't. Anyway, I would not know this personally if not for the fact I had a job interview once upon a time where I was asked to give a lecture on combinatorics. I have never taught a class in combinatorics, so this is like the most miserable job interview possible, Here, go give a lecture on something that you've never taught before and you're not an expert in. Okay. But one of the things I learned in my preparation for that talk was that Venn diagrams only work for 3. So there you go. This matters if you're looking at counting problems, which we will look at later. So, all right, let me move on here. So the next theorem is let U be universe of discourse, and let's let A and B be subsets of that universe. Then here's some handy-dandy properties of complement. What's the complement of the complement? I heard an A. Very good. What is the union of a set and its complement? The universe. Very good. What is the intersection of a set and its complement? The empty set. Very good. What is the difference, set difference of A and B? That stopped you guys for a second, huh? So complements reverse inclusion. B complement subset of A complement. So like if A is a subset of B, then it means the complement of B is a subset of the complement of A. So they turn, complement turns subset around. Now A, let's draw a picture of A minus B to see what we're going to write down. So if this is the universal set, right? This is the universal set. Suppose, who put that there? So here's A, right? Here's B. So A minus B, A minus B is what? That's inside the blue, right? What's the complement of B look like? Right? This is everything outside, right? That's B complement. So what could you say here? A minus B, how does it relate to B complement in A? Very good, yeah. So A intersect B complement. I hope that's what's in the notes. Yeah, okay. Phew. Wait a minute, were you looking at the notes? Okay, good, all right. I mean, it's not the worst thing to be looking at the notes, but it's more fun to discover it for yourself, right? All right, so that's E. F is that A union B complement is equal to A complement intersect B complement. And G is that A intersect B complement is equal to A complement union B complement. I'm not entirely happy with the way the tildes look in my notes. Like, I'd like for them to be bigger in places. Sorry, they're kind of hard to see some places. I would like to blow up the tildes a bit if I could, but it is what it is. Now, finally, H, we have A intersect B is equal to the empty set if and only if A is a subset of what? For the picture I have right above, what would it take for for A and B not to meet? A would have to be a subset of what?
Not B.
Not B, or B complement's what we call that, yeah. But yeah, other people might call it not B. That exposes a deeper thing, which is that there's an obvious correlation between the set theory we're doing and the laws of logic we talked about before, right? And so essentially for that reason, what do you think these two laws of set theory are called? What are these called? De Morgan's laws, yeah. Because if you try to prove these, they essentially rest on De Morgan's laws. All right. Let's see here. Yeah. So the proof of part E is like problem 33 in your homework for what it's worth. All right. Let's see here. Let's see if we can prove. Let's talk about the proof of like, well, half of the proof of F. How about that? Half of it, all right? So let's let X be an element of the complement of A union B, right? So that means that X is an element of, excuse me, X is not an element of A union B, right? In other words, symbolically, what's that? That's not there exists X, A union B, right? My bad, X. I think I could write it this way with the symbolic logic, right? I'll put this as a parenthetical comment here, right? That's a way of writing this symbolically is that, right? And what did we learn about? This is what? We can read, that's what, for all X? Oh, I'm sorry, let me stop this. This is not helpful. I always make stupid mistakes exactly at this point in class. If you study all of my lectures ever, when I get to the 40-minute mark in a Tuesday, Thursday class, I do dumb stuff. Like, it's just a feature of my existence. But anyway, so if X is not an element of A and A union B, what does that mean? X is not an element of A, right? And X is not an element of B. Like, let's not overcomplicate this. This is just basic logic, right? Do you guys agree? For it to be in the union, it's in A or B. So if it's not in the union, it's in neither A nor B. I think the logic of that sentence is actually De Morgan's law of logic. But anyway, what's this mean then? Thus, X is not an element of A intersect B, right? Therefore, X is an element of A intersect B complement. Which proves half of part F, right? Namely that the complement of A union B is a subset of the intersection of the complement of A and B. All right. I have a remark on page 40. If you read it, I actually give the remark on page 40, I think it gives a legitimate, which you might call biconditional proof. So there's the other way to prove two sets are equal is just to prove that they have the same elements. So I think if you read the remark on page 40, you'll see I have an argument there which shows you that that the complement of A intersect B and the union of the complement of A and the complement of B are actually two sets which contain the same elements. And if you can give an argument which shows that both sets contain the same elements, that proves that the sets are equal by one of our basic axioms. I think extensionality, is what we called it. All right, so let's move on here. So I think I've shown you guys enough of these sorts of proofs that you should have a good shot at doing the corresponding homework problems. It's just stringing together definition of union and intersection, set difference, and subset and so forth. So what's next in the notes is a discussion about families of sets. So we should talk about that. What's a family of sets? Well, for us, it's a set of sets, but we will avoid the temptation to say, but what about the set of all sets? Like, we're not going to talk about that. So it's kind of like when I had a Bible study in my undergraduate. I had a Bible study with Campus Crusade at the time. In every Bible study, we would end by saying that, like, next time we'd talk about predestination. So, like, they had, like, some rule to not talk about predestination in the Campus Crusade Bible studies, which seems like, in retrospect, really, really dumb. But yeah.
For your proof of F, is the conclusion wrong?
Uh-oh.
Does it seem to prove that
Um,
not A and B is equal to
X
A and B?
is not an element. Is my conclusion wrong? Let's see here. Probably. Let's see here. Something's wrong. So if X is an element of this, which is to say that X is not an element of A union B, I think we're fine with that. So X is not an element of A, and X is not an element of B. So what does this mean? This means, I'm an idiot. That's what it means. So this means that, I'm going to double up on my hints. X is an element of A complement, and X is an element of B complement, right? That's what this means, right? Obviously. Not obvious to me 3 minutes ago, but there it is. Then what? Consequently, what? X is an element of A complement intersect B complement, right? Because it's in both of the complements, which means it's in the intersection of the complements. Therefore, A union B complement is a subset of A complement intersect B complement. That is the half of the proof I was aiming for. So thank you. Very helpful as always. Did I do anything else? Okay. I really do appreciate corrections in class. They are very, very valuable to me and also to your peers, you know. We all leave here less confused. That's good. Okay, so families of sets are sets of sets. So like here's a definition. Definition. Let triangle not equal to the empty set. All right. If there exists a set A sub alpha for each alpha in the big triangle, then A equal to A sub alpha such that alpha is in triangle, all right, is a family of sets. It's a family of sets indexed by a triangle, apparently. The elements of triangle are called indices in this context. All right. So, for example, so this, if you don't like the triangle, a lot of times I might put the triangle equal to like a uppercase lambda like this sometimes. Other times the triangle, it might just be like the natural numbers. That's not uncommon. For example, what example am I on? I've lost track. 3? 4? If I choose 10, I think we're good. What about 5? Okay. So as to not offend the OCD among you, 5. Let's see here. So I could let, for instance, A equal to 0n such that n is a natural number, right? That's a family of sets, right? Yeah. I could, here's another family of sets. I could do something like, pi minus delta, comma, pi plus delta, such that delta is an element of 0 to infinity. So the first set, the index is just like it has a natural number index. So like a sub n would be 0n, for instance. In this one, my typical member of this family of sets, I might call b sub delta, pi minus delta, pi plus delta, right? In this case, the index is an arbitrary positive real number, right? These are very different families, obviously, but you can look at a family of sets, all right? If we have a family of sets, we can do things like study the union or the intersection over a family, all right? So let me define that for you. So definition, given family of sets, let's say A sub alpha for alpha, and I'm going to use capital lambda this time because the triangle is wearing on me. We define union over alpha in lambda of A sub alpha equal to x such that there exists alpha in lambda with X an element of A sub alpha. So the union over a family of sets, it's simply the collection of all elements which the elements in at least one of the sets in the family. So this is union. What do you think intersection should be? What's the intersection over a family? X such that what? I'll start us out. X is an element of A alpha for all what?
Alpha elements of the.
That's right. Which is a fancy way of saying that it's in every single member of the family, right? X is in every member of the family if it's in the intersection. So it's so commonplace in mathematics to have the case that the index set is the natural numbers. We have special notation for that case, all right? So like, let me just, let's write that down while we're at it here. Special notation, special case. Lambda equals to n, then we have like union over alpha, well, union over I so my bad, I'll get it eventually, guys, here. Union over n in lambda of like A sub n, we just write that union n equals 1 to infinity of A sub n. And, intersection over n in, this choice of lambda, we just write intersection n equals 1 to infinity of A sub n. A lot of the interesting problems come from the case that our family is indexed by the natural numbers. All right? So, let's see here. So I probably won't prove any of these today, but I want to just throw some out there for you. And we'll probably, next class, try to prove something of this realm that's not easy. But here's one that's intuitively clear, but the question is, okay, so intuition's great and all, but what if you actually want to prove these things? How will you prove these assertions? Well, that we'll come back to that next class, okay, guys? But if we let A sub n be 0 to n for n in the natural numbers, then we can show that the union n equals 1 to infinity of A sub n, right? Which I can let me just rewrite it again. N equals 1 to infinity of 0 to n. What do you guys think that's going to be? In contrast, what would the union n equals 1 to infinity of, say, A sub 1 over n be? I guess I haven't really defined A sub 1 over n, but let me just write it out. I'll do it like this. I mean, technically speaking, my current notes aren't quite right because I look at A sub 1 over n, but I haven't really defined that in example 3.34. So there's arguably a typo there, or something worse. But anyway, so you guys tell me, what do you think is going to be the answers